Okay, so let us now do some exercises. So the first one, let X be a set, R a ring of subsets of X. Let S equals set of all F subset of X such that F belongs to R or F complement belongs to R. So the set contains all elements of R and their complements. Okay, show that S is the smallest algebra containing R. So solution. So if S dash is any algebra containing R, then it contains all complements of members of R as well. So thus S is contained in S dash for any algebra which containing R. So enough to show S is an algebra. So phi belongs to R implies phi belongs to S, empty set belongs to S, and therefore this implies and also so this implies X belongs to S because it's a complement of phi and therefore X belongs to S. Okay, now enough to show, we have already seen this, S is closed under finite unions and complementation. So closed under complementation is obvious by construction, because if any member of S, either it's a member of R, in which case its complement is also in S. If its complement, if it's not in R, that means its complement is in R and therefore it's also in S, that member also. Okay, the complement is also in R, S. So this is obvious by definition. So now we have to show that it's closed under union. So let us take EF belong to S. So to show E union F belongs to S. So let us look at different cases. So first case, so if E and F belong to R, this implies E union F is in R, and that implies that E union F belongs to S. Second one, if E complement F complement belong to R, so both of them are such that the complement is in R, so this implies that E complement intersection F complement belongs to R, that is E union F complement belongs to R, that is, which implies that E union F belongs to S by definition. The complement is in R, therefore it's in S. Then 3, E belongs to R, and let's say F complement belongs to R. This is the third possibility. So then you have F complement minus E belongs to R, because the difference of a sets in the ring. So this is nothing but, this means, what is F complement intersection? It is F complement intersection E complement belongs to R, that is E union F complement belongs to R, which implies that E union F belongs to S. So in all the cases we have shown that the union is in S, it's closed under complementation, it is closed under the unions, and therefore it is an algebra, and it's in fact the smallest algebra containing R. Okay, so second problem. Let X and let E be a subset of X. Given, fix it. Let E equals set of all F contained in X such that E contained in F. So it's all sets which contain E, so that is a collection. Compute R of E. Compute the ring which is generated by this. So solution. So clearly X belongs to E. So this implies that R of E is an algebra. Okay. So that means it has to be closed under, so implies closed under complementation. So this implies that R of E contains set of all F in X, F E contained in F, that is nothing but the elements in E, union their complements. So set of all F contained in X such that F is contained in E complement. That means F complement is contained in E. Okay, so this is the the other part. So enough to show let us call this as S which contains E anyway is a ring. In fact it's an algebra, whatever we want. Okay, so it is closed under complementation, and therefore enough to show, so if E union F so enough to show EF, let us not write E because E is a given set, FG in S implies F union G belongs to S. So again we have to take the three cases, and now in fact if F or G contains E, then the union F union G contains E, implies F union G belongs to E, and therefore it is already in S. So we have to take the only, so both of them should not be contained in E. So if containing E, so F complement G complement, so FG contained in E complement. Okay, so this implies E contains F complement, E is contained in G complement. So this implies that E is contained in F complement intersection G complement, which is equal to F union G complement. Okay, and this implies that F union G is contained in E complement. Okay, because you take the E is contained in, so F union G is contained in E complement, and this implies that F union G is contained in S. So this, it becomes an algebra and this. Third one, X non-empty set, R a ring on X, mu a measure on R. EF belong to R, show that mu of E intersection F plus mu of E union F equals mu E plus mu F. So solution. So what is E union F? I can write this as E minus F union F. Okay, so this is E, this is F, so this is E minus F, and this is F, and that will be the union of, so, and this is F minus E, and this is E intersection F. Okay, so this can be written, and this is disjoint. Okay, similarly, E minus F union E intersection F. So E minus F is this, E intersection F is this, and that is equal to E. Again, this is disjoint. Okay, so if mu E or mu F equal to plus infinity, then mu of E union F, which is bigger, is also plus infinity, and so star is obvious. So we have to show this equation, that is star. So we can assume that mu E, mu F are both finite, and this will imply that mu of E minus F, which is smaller than mu E, is also finite. Okay, so now by additivity, because countably additive is also finite additive, so mu of E union F equals mu of E minus F plus mu F, and mu of E minus F plus mu of E intersection F equals mu E. So add and cancel mu of E minus F, which is finite, remember. So I'm allowed to cancel, and everything is finite in this equation, and that proves the solution. For X non-empty set, R a ring on X, and mu greater than or equal to 0, finite additive set function on R, which is continuous from below at every E in R. What does this mean? That is, if EI belongs to R, EI increases to E, then mu E equals limit n tending to infinity mu of En. Show that mu is a measure. So solution, mu is finite and finitely additive. Additive means finitely additive. Therefore, mu of E equals mu of E union phi equals mu E plus mu phi. I can now cancel mu E because it is finite, and therefore this implies that mu phi equal to 0, since mu E is finite. I couldn't have cancelled if mu E were infinity, both sides are infinity, and that tells you nothing about mu phi. Okay, so that is why mu phi is 0. So mu is non-negative, mu phi is 0, so we only have to show countable additivity. So En, n equals 1 to infinity, disjoint sequence in E, and E in R, and E equals union Ei, I equals 1 to infinity is also in R. And now we have to show countable additivity. So you take Fn equals union I equals 1 to n Ei, and this implies, because it's a ring, this belongs to R, and Fn increases to E. Okay, so mu E equals limit n tending to infinity mu of Fn, because it is continuous from below. This by additivity is called sigma I equals 1 to n mu of Ei, which is nothing but sigma I n equals 1 to infinity mu of E. Okay, so that proves that result. Okay. Five. X non-empty set, S a sigma ring on X, mu measures. Now you define lim inf En, n tending to infinity. So En, n equals 1 to infinity in S. Okay, this definition is union n equals 1 to infinity intersection I equals n to infinity Ei. Okay, so show that lim inf n En mu of this is less than equal to lim inf mu of En. This is a very useful, very important inequality, and therefore it is good to know this. Okay. So solution. So let Fn as usual be equal to intersection I equals n to infinity Ei. And let us take E equals lim inf n tending to infinity En, which is equal to union n equals 1 to infinity Fn. And then Fn, because you are taking intersection over smaller and smaller ranges of the values of I, so Fn increases to E. Therefore mu of E is the limit as n tends to infinity of mu of Fn. But Fn, by monotonicity, this is less than equal to mu of Ei for all I bigger than or equal to n, and therefore mu of Fn is less than or equal to inf I bigger than n mu of En. Now, what is limit of mu of Fn? Mu of Fn is an increasing sequence, and therefore mu of Fn is also increasing, and therefore this is by definition supremum over all n mu of Fn. Okay, so mu of Fn is less than this. Mu of E is the limit of mu of Fn, so mu of E is less than equal to supremum over all n, and then mu of Fn, but mu of Fn is less than inf I bigger than or equal to n mu of Ei, and that's precisely lim inf by definition mu of En. Okay, so